Hello, champs. How are you? So today we're gonna start with the topic of electricity and magnetism. So basically, our agenda will be to get an overall picture of what the chapter looks like and what are the important aspects that you need to consider in both, right? So since we have a very small duration, we will have the session for about an hour. So we'll discuss all the essentials that are required for this particular concept and we'll also discuss some nitty-gritties, right? What are the things that you need to know? What are the things you need to avoid and so on and so forth, right? So without further ado, let's start our discussion on the topic of electricity and magnetism. So here is our screen. I hope it is visible to all of you. So let me make myself a little bit bigger. So just do this. Fine. So students understand when we hear this term, which is called electricity, the first thing that comes in our mind is the concept of charge. So the first thing that comes in our mind is the concept of charge. Now, what is the concept of charge? So charge is like an emotion of a matter. It's not a quantity. Don't think it like something that is tangible. It's like happiness, sadness. So it's a property. So first of all, charge is what? It's a property. Charge is a property. So what this property does? This property applies force. Meaning, if you have an atom here and you take one electron out from this atom, it gets a positive emotion. And if you add one electron to this atom gets a negative emotion. As an outcome, what happens? If you bring these two emotions together, they attract each other. So what is charge? Charge is an emotion that arises due to excess or deficiency of electrons. If you have excess of electrons, we call it negative charge. And if there is a deficiency of electron, you say positive charge. So when you bring two bodies which have same kind of emotion, same kind of charge, they repel each other. So meaning if I bring a positive and another positive together, they repel. But if I bring a positive and a negative together, they attract. And if I bring a negative and another negative together, they repel. So what we understood? This here is a property by virtue of which they apply force on each other. How that property arises? By excess or deficiency of electron. What we name that property as charge. So if I'll ask you a very basic question, that what is the shape of charge and what is the color of charge? If I ask you a very simple question, what is the shape and color of charge? Then you may say spherical, round, blue in color, white in color, depending on what color they show you in the textbook. But remember, that's the color of the element or the atom you have. It's not the color of charge. Charge is a property. It's like happiness, sadness, joy, right? So charge is an emotion. It doesn't have a shape, and it also does not have a color. Now there are few more things about charge. For example, if you take an electron, electrons have negative emotion, which means basically negative charge. How much of that negative charge? So that is 1.6 into 10 raised to the power minus 19, but any quantity which you describe as a unit. So the unit for this is coulombs. So what is the unit of charge? Coulomb. And what is the charge on one electron? It's a negative charge, first of all. If you want to put a sign, you can put a sign here. And the value is 1.6 into 10 raised to the power minus 19 coulombs. Unit is very important, coulombs. On the other hand, if you take a proton, that also has an emotion. And that's a positive emotion. Positive. And the value of that charge is plus 1.6 into 10 raised to the power minus 19, again coulombs. So do electrons and proton have same kind of emotion, same kind of charge? Yes. What is the value? 1.6 into 10 raised to the power minus 19. Electron has negative and proton has positive. So now you will be able to guess that if I bring two electrons together, they will repel each other. And if I bring a proton and an electron together, they will attract each other. So likes repel, unlike attract. So we understood this property of charge. Next property of charge is a scalar. Charge is a scalar quantity. Now, what do you mean by charge is a scalar quantity? If I tell you that you have to go to a certain shop in order to buy some clothes for you. If I tell you that shop is 2 kilometers away from here, you may be able to reach there, you may not be able to reach there if I don't give correct directions. That goes straight for 1 kilometer, take a right, and then you'll be able to reach there. But there are few quantities where I don't need to tell you the direction. For example, if I say go to the shop and buy 2 kg potatoes, you'll go to the shop, you'll buy 2 kg potatoes, you will not tell 2 kg to the right, left, or so on. So any quantity that requires direction for its complete description is called a vector quantity. On the other hand, any quantity that has a number only for its description with a unit, then that quantity is called a scalar. So when I was telling you about a charge, I told you two things. One is the number, could be positive or negative, and a unit, which is coulombs. I didn't tell anything else about it. So that means charge does not require direction for its complete description. And that's why charge is a scalar quantity. Next property of charge is conserved. Now, what do we mean by charge is conserved? When we say total amount of energy in this universe is conserved, that law is called law of conservation of energy. What does that mean? That means the total amount of energy supplied and the total amount of energy utilized, that will always be the same. Similarly, when we say law of conservation of momentum that you study in grade 9, we say that the initial momentum is equal to final momentum under certain conditions. Similarly, when we say charge is conserved, meaning charge can neither be created nor destroyed. Charge can neither be created nor destroyed. Meaning, if I have a neutral atom here and a neutral atom here, that means they don't have any excess of electrons, they don't have any deficiency of electrons. If I transfer one electron from here and place it there, you may say the first one gets a positive charge because there is a deficiency of electron. And the second one gets a negative charge because there is an excess of electron. Now, if there is a deficiency of electron in the first one, you will say that, okay, first one is acquired charge, charge is not conserved. Initially, the number was equal, the atom was neutral. But the moment you transferred one electron, there is charge now, so charge is not conserved. How can you say charge is conserved? But then I'll say, see the other atom as well. There also the number of was equal, like number of protons was same as number of electrons. But when you added one electrons to it, the number changes. Now the number of electrons are extra. So if initially there were 10 electrons here and 10 protons, here also 10 electrons, 10 protons, then if you transfer one, here it becomes 9 electrons and 10 protons. But remember, here it becomes 11 electrons and 10 protons. So if you take both of them together, then the net amount of charge is still the same. I hope this picture is clear. Charge is conserved. Now I'll give you a question and you'll have to think about it and answer in the comments. The question is mass conserved? So the question is mass conserved? So that's a question you can answer in the comments. Energy is surely conserved. I'm asking about mass. One more property about charge, that's a final property that we'll discuss. And that property is the property of quantization. So charge is quantized. Now, what do we mean by charge is quantized? If you go to buy, let's say, a chips packet, right? So you can buy 1 packet, 2 packet, 3 packet. You cannot say to the shopkeeper that open the packet, take 2 chips out and give it to me, right? So if you want to buy a chips packet, a chocolate, you will have to buy it as a minimum quantity. Like you'll have to buy a minimum 5 rupees packet. You cannot go below this. So quanta here means packet. Quanta here means packet. So when I say charge is quantized, that means you can transfer charge only in form of packets. Now, what do you mean by packet in case of charge? So why we have charge? There was a neutral body, same number of electrons and protons, and then you transferred 1 electron or you gave it 1 electron, right? So you either took 1 electron out or you gave 1 electron to it. So what is the unit that you are transferring here? An electron. So quanta means packet, and a packet here means an electron. So if charge is quantized, you can transfer 1 electron, you can transfer 2 electrons, you can transfer 3 electrons, you can transfer 4 electrons, you can transfer 5 electrons, you can transfer n number of electrons. You can transfer n number of electrons. So can I say charge on any body, Q? This will always be either equal to the charge on 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, 6 electron, or n number of electrons. It can never be half electron, 3 by 2 electron, root 2 electron, and so on. It can never be a fraction. Why? Because you cannot open the packet. If you want to buy, you'll have to buy the whole packet. So charge on substance, right, will be always be n times charge on an electron. Now this could be positive or negative. So sometimes you can also write it like plus minus n. So I hope this is clear that what is charge quantization. So charge quantization basically is that you can transfer charge only in form of packets, and 1 packet here represents electron. So let's solve a few questions to understand this better. So let's say question number 1. A friend of mine came to me and told that I have an atom on which the charge is 1.6 into 10 raised to the power minus 20 coulomb. Now I'll have to take a call whether the person is telling the truth or it's a lie. So give it a thought and answer it in comments. When I'm saying the charge is 1.6 into 10 raised to the power minus 20, I'll have to wait for a while and think. What's the charge on 1 electron? Or what's the charge on 1 proton? Or what's the positive or negative charge it acquires? So this will be 1.6 into 10 raised to the power minus 19 coulomb. Meaning, the charge my friend is talking about is less than the charge on an electron. And you cannot go below the value which is like having a charge on an electron, because you cannot open it up. The minimum you can get is 1.6 into 10 raised to the power minus 19. You have 10 raised to the power minus 20 here. So my friend is telling a lie, and this thing is not possible. I hope you also guessed it right. Next question. Let's go to the next question now. So the next question says a body is neutral. Now you know if you remove 1 electron, it gets a plus of 1.6 into 10 raised to the power minus 90. Proton becomes extra. And if you add 1 electron, it gains minus 1.6 into 10 raised to the power minus 90. So I want this body to have plus 1 coulomb of charge. I want this body to have plus 1 coulomb of charge. So how many electrons are required to be transferred? So let's assume I have n electrons which can give me this value. So first question that arises whether I need to add or remove. So I want a positive charge, so I need to remove, because addition of electron gives you negative charge and removal gives you positive. So I know formula is Q is equal to N times E, positive, because I want a positive charge. Q I want is 1 coulomb. N is something which I want to calculate. And E is 1.6 into 10 raised to the power minus 19 coulomb. Now remember, what I want to find out? N, the number of charges that I need to transfer. So if I cross multiply this thing, then N becomes 1 divided by 1.6 into 10 raised to the power minus 19. And when you simplify this, you'll get it around 6 into 10 to the power 18 electrons. Now wait for a while here. This value is huge. You need to remove 6 into 10 raised to the power 18. That means you have after 6, 18 zeros. That is why 1 coulomb is a huge unit. So generally, whenever they give you charge in questions, they give you either written like microcoulomb, nanocoulomb, picocoulomb, and so on. Now, what is micro? Micro stands for 10 to the power minus 6. Nano stands for 10 to the power minus 9. And pico stands for 10 to the power minus. So there will be very small values of charges that you get in the questions, because 1 coulomb is a huge amount of charge, right, which you need to have. Now, once we understood what the charge is, the next thing that we need to understand is what is current. So the next thing that we have is what is current. I hope up to this point everything will be clear. So what is current? Current is the rate of flow of charge. It's not just flow of charge, it's rate of flow of charge. Now you will say, what's the difference? So understand, if I say rate of change of displacement, what you do? You divide displacement by time. If I ask you what is rate of change of velocity, what you do? You divide velocity by time. Then if I ask you what is rate of change of momentum, you divide momentum by time. So rate of change of anything means you divide that quantity by time. So if I say rate of flow of charge, that means current is charge divided by time. So current is divided as charge divided by time. Unit of charge is coulombs and unit of time is seconds. The other name for coulomb per second is ampere. So if we say unit of current is coulomb per second, is it wrong? No. But can I say, is it ampere? Is it wrong? No. Both are correct. They are two names for the same thing. What's the unit that we use? So unit of current is amperes. So for example, if I say that charge that is flowing is 1 microcoulomb, and this happens in, let's say, 1 second only, and I want to find out what is the current, you will say, okay, I is Q by T. So Q is 1 microcoulomb, time is 1 second. Micro can be written as 10 to the power minus 6 divided by 1, which can be written as 10 to the power minus 6 amperes, which can also be written as 1 microampere. I hope there will be no issues up to this point. Simple. Now, sometimes they play around with this a little bit. What they do? They will say that, okay, number of charge particles that are being removed are 10 to the power 3, or the number of charge particles that are moving at 10 to the power 3. And then they say the charge on an electron is 1.6 into 10 raised to the power minus 19. And this happens in, let's say, 1 microsecond. So if I'll ask you what is the current, although this number is very less, this can go like very big, 10 to the power 18 and all. But let's say for our purpose, we are taking it like this. So then what you will do, first of all, you don't know what is the amount of charge you have. So first you need to calculate what is the amount of charge you have, and that is N into E. Then you divide it by T, and then you will substitute the values. So you will say 10 to the power 3 number of charges are overflowing. Each charge has value this divided by 1 into 10 to the power minus 6. And then this will give you your. Now, if you want to simplify this, of course, you can write 10 to the power 3 into 1.6 into 10 raised to the power minus 19. And this will go up, so it will become plus 6. So you have in plus 3 plus 6, and then in minus 19. So this becomes 1.6 into 10 raised to the power minus 10. You can have different values, and this is how you will solve question in accordance with that. Sometimes they also ask you define 1 ampere. Define 1 ampere. Now, what is the big deal with this? I is Q by T. So if I take Q as 1 and T as 1, isn't it 1 ampere? So if I know this thing, what is the big deal in defining 1 ampere? You will say, when a charge of 1 coulomb flows in 1 second, then the current will be 1 ampere. Simple, easy. So I hope all of you are clear about concept of current. So what did we discuss from starting? What is charge? What type of charges you have? Removal of electron gives you what charge? Addition of electron gives you what charge? Then some properties, scalar, quantization, charge is conserved. Then finally we discussed current, its unit, and how to solve numericals associated with it. Now I'm not discussing it here, but they can give you current and time, and you can find out charge using that. So it's just a cross multiplication thing, nothing else. After current, the property that comes is called potential. So let's try to understand then what is potential. In your batteries, right? Batteries that you use at home, you will find something like 12 volt, 24 volt and on written over it. So if a battery says 12 volt, what does that actually mean? So 12 volt means the battery is capable of doing 12 joule of work on 1 coulomb of charge. So what the battery is doing, it's pushing the charge in the loop, no, the circuit. So potential is the amount of work battery can do in order to direct charges in a particular way. So 12 joule of work for 1 coulomb. If I have, let's say 2 coulomb, then the amount of work will become 2 into 12. 3 coulomb, then the work done will become 3 into 12. 4 coulomb, the work done will become 4 into 12. Then if I have Q coulombs, then it will become Q into 12. And if my potential is V instead of 12, then work done becomes Q into V. So is it something alien? No, it's the amount of work the battery can do on 1 coulomb. If you have Q coulombs, then you multiply Q with the potential. Now from here, you can define potential as W by Q, where W represents work done and Q represents charge. So if I have to write down the definition for work done, I can say work done per unit charge, work done per unit charge is called potential. Work done per unit charge is called potential. So formula is W by Q. Unit for work done is joules, unit for charge is coulombs. And joule per coulomb is also called volts. So it's not very different actually. At our homes also, generally we used to have two names. One is what you use in school and for all official purposes. And the other one is what your parents used to call you at home. So that's why these quantities also have like 2 units, right? And basically the other reason is they will have to give the units in the name of some great guys. So that's why you have this complication here. So unit of volts is, potential is volts. So if I'll take up a question that the battery is capable of doing 36 joule of work on 3 coulomb of charge, then what is the potential? You will, so it's a piece of cake, sir. So you will say that this is 36, which is the work done, and divided by charge is 3. So this will become 12 volts. Similarly, I can give you a question. I'll say that, okay, there is a battery and that has a potential of 24 volts. And it's given that the charge is 3 coulombs, and find out the potential, find out the work done. So you will say, okay, this is also not tough because I know potential is work done by charge. So I can write down the work done as potential into charge. Potential is 24 into 3, and that will be your answer. But remember, work done's unit is joule and unit for potential is. If they ask you to define 1 volt, what's the big deal? You will simply say that if work done is 1 joule and the charge is 1 coulomb, then the potential is 1 volt. Simple. So what we discussed what is charge, what is current, and now we discussed potential as well. So now I'm going to talk a little bit about the conductor. So the wire. So let's discuss a little bit about the wire. If you take a metallic wire like this metallic wire has charges in it. And due to thermal agitation, it's not like they are at rest, they are moving. So you can imagine it like there is a room. In that room, you have bunch of small kids, toddlers, they are playing there. So if I'll say they are moving, you will say yes. But if I'll ask you, is there a definite pattern which they are following in their movement? The answer is no. That is why when you hold a wire without connecting any battery, you don't get any current because flow is there. But net flow in any particular direction is not there. The moment you connect a battery to it, battery has a negative terminal, it has a positive terminal. What the battery gives is, if this was an electron which was moving like this, and this was the electron which was moving like that, and there was no resultant net flow, now positive terminal of the battery will attract this electron as well as this electron, and negative terminal will repel them. So the electron which was moving to the left, it will still move to the left because it is getting pushed in that direction. But the electron which was moving to the right will also get pushed to the left now. So will there be directed motion now? Yes. So battery does not provide charges. So battery is a source of energy, not charge. So if somebody tells you that battery is giving charges, that is why there is current. No, charges are there in the conductor. Kids are there in the room. You want a PT teacher. So battery is like that PT teacher who aligns them in a particular way and let them move in a particular direction. So battery is a source of energy. It does work. It pushes them in a particular direction. And when you get net flow, you get current. But there is a catch here. Let's imagine that you are running towards a wall. But being human, you know, if I'll get stuck to the wall, then I'll get hurt. So you'll change your route and you'll follow a different route. But electrons don't have brains. If they are running in a particular direction as told by the PT teacher, their battery, they'll move in a straight line. If another electron comes in front, they don't have brain to go around it and go straight. They will just collide with the other electron. They'll collide with the lattice structure. They'll collide whatever comes in front of them and lose energy. So whenever current tries to flow through a conductor, there are restrictions. There are collisions. So opposition to the flow of current is called resistance. Why there is resistance? I just told you resistance is there because sorry for the interruption, guys. There was a very important call. But opposition to the flow of current is called resistance. Opposition to the flow of current is called resistance. So whenever electron tries to move, not having brain, it will collide with lattice structure electrons and all, and it will lose energy. And it will oppose the flow of current. When we try to figure out on what factors this resistance depends, then we got to know that R depends on L. The longer they move, more will be the collisions. Common sense. R is inversely proportional to area. The larger the area they have, more freely they can move, more mobility. So less resistance, less collisions. When you combine these two, you get R proportional to L by A. And whenever you remove proportionality sign, all of you know this, we introduce a constant. So the constant here is rho L by. So resistance depends on how many factors? Resistance depends on the length of the conductor. 2-meter wire will have more resistance than wire of 1-meter length. Resistance depends inversely on area. Meaning 1-meter square area will have more resistance than 2-meter square area because they're inversely related. So 2-meter square area, if you have, you get certain value. If you reduce the area, resistance will increase. And if you increase the area, resistance will decrease. Is there anything else, sir, on which the resistance of a conductor depends? Yes. So resistance of a conductor also depends on temperature. Now you may say, sir, if I raise the temperature, will the resistance increase or decrease? So temperature increase will give a rise in resistance for a conductor. For a conductor. Meaning, if you have a congested road, there are already too many vehicles. They were not having mobility to move. Now what you did, you brought few more cars and you are expecting those cars will move freely. They won't be able to. They won't be able to move freely. Why? Because there is already traffic. There is a lot of congestion. And if you are bringing more charges by increasing temperature, because what will happen if you raise the temperature, more charges will lose their atom and will become free. And more the number of charges getting freed, more will be the charges that you will have in the space for movement. Now the space is fixed. So they will collide more and hence resistance will increase. Now, what kind of questions they can ask you on this? So they can say that if the area becomes twice, what will be the resistance? If length becomes twice, what will be the resistance? And so on, right? Although I'll expect you to remember two formulas, right? If stretching of wire happens, then its length changes and its wire also, like wire's area also changes. So in these cases, remember for this, like we have a very short duration to complete a lot of things, but I'll tell you the formula and the logic behind it. You can work out like the remaining things on your own as well. So when stretching happens, actually you are trying to change the dimension of the wire without changing the actually quantity of the wire. So density is still the same, volume is still the same, mass is still the same. So if you try to increase the length, area will reduce proportionally. So if you say R1 by R2 is equal to L1 by L2, you are not right because you didn't take into consideration the change in area. So in these cases specifically, if they ask you what is the ratio of resistances, then that will be equal to L1 by L2 whole square and that will be A2 by A1 whole square. Now this is a homework for you, and if you get the result for this, please tell me in the comment section. And the homework is you'll have to prove the above thing on the basis of initial volume will be equal to final volume, where initial volume is L1A1 and final volume is L2A2. Because the total volume will remain the same for the substance. You're not changing the substance, you're just changing its dimension. So now we understood like three very important components, like what is potential, what is current, what is resistance, what are the factors on which current depends, and what are the factors on which resistance depends, and what kind of questions that can be asked. Now, if I combine these in a proper format, that is what you call a circuit. So a circuit is a combination of these elements. So in a circuit, what you will have? So if I talk about a circuit, in a circuit, what you will have? First of all, you will have a resistance, which we represent with zigzag lines. Then you will have a battery, which will have a long line, which is positive terminal, a short line, which is negative terminal, that gives you potential. You can have a key that you can use for opening and closing. And then you can have an emitter if you want to measure current. You can also have a voltmeter if you want to measure voltage. Now remember just two things about emitter and voltmeter. Emitter is always connected in series with the element where you want to measure current, and voltmeter is always connected in parallel to the element where you want to measure the voltage. So if by connecting battery V, I get a current I, then charge has started like from some energy level. So if let's say I am saying that here the charge had 0 energy, you can take any value you want. Then when it crosses the battery, it has acquired V amount of energy because the battery gives energy. Now with this energy, it tries to move, and the movement of charge is called current. When it reaches here, it will have to have collisions now in order to cross. So when it crosses and reaches here, it will lose some amount of its energy. Again, understand, before collision, the electrons were having some amount of energy. When they go through the conductor and collide and come out, they lose some amount of energy. So there is a law called Ohm's law. There is a law called Ohm's law, which tells us about if a charge, or you can say flowing charge, you can say current. If current flows through a resistor, so if current flows through a resistor, let's say the value is I and the resistance is R, then the potential drop means how much energy the resistance will take, the collisions will take. So that potential drop can be written as I into R. So what V represents here? V represents here the potential drop. V represents the potential drop, and that is I into R. So for example, if I say that there is a current of 2 amperes flowing in a resistor of 10 ohm, then the potential drop becomes 2 into 10, which is 20 volts. And that is your. So Ohm's law tells us how much will be the drop in any given resistor if the current is I. Actually, the law is not like explained in this way. So how it's written in your textbook, they write it, potential drop across a resistor will be directly proportional to current. Now, few of you may say, some books say that I is proportional to V. Actually, its I is proportional to V only. Right? Actually, in reality, I is proportional to V only because I is the independent variable and V is the dependent variable here. V is what you change and I is a consequence changes. But in your textbook, it says V is proportional to I, and whenever you remove proportionality constant, you'll have to introduce a constant, and that constant here is the resistance. So is it the same thing? Yes. Just written in a slightly different way. So Ohm's law says potential drop across a resistor will be directly proportional to current at a constant temperature. At a constant temperature. Now, why do they say at a constant temperature? Because with temperature, the resistance changes. So the constant will change. Is it applicable all the times? No. If the temperature changes, Ohm's law will not So this helps us in finding out current if we know the resistance. Now, next thing which we have, it's very important, and you will have to like understand it with a lot of focus, and that is finding out equivalent resistance. Equivalent resistance. Now, what do we understand by equivalent resistance? Whenever you are saying, I want to replace a bunch of resistors with a single resistor, then you are trying to make sure that the input and output are not changing with that. So for example, if I have a laptop and I make it smaller, I want to make it smaller. So I want to make it smaller, that's a point, but I don't want to compromise on the functionality part of it. If my laptop starts working like a washing machine, it will not serve the purpose. So you have a bunch of resistances, you want to convert it into a single resistance, but without changing voltage and current. Because if voltage and current changes, then in that case, your whole circuit will change, your input output will change. So let's say if I have a bunch of resistors like this, R1, R2, R3. Let's start with 2, then you can generalize it for 3 as well. And I want to replace it with a single resistor. But remember, I don't want to change my voltage and current, because if my voltage and current changes, no use. So if I want to do that, I'll say, okay, there was a battery potential V, there was a current I. So charges had energy V. They went through R1. So they started with 0, right? Since these points are connected, so there is no resistance. So they will have 0 only. So they started from 0, they got V. Then from V, they gave some energy to R1, and Ohm's law says the given energy is I into R1. Then they give some energy to R2, that is I into R2. And finally, they come back to from where they started. So imagine this V is like the amount of money you have. So you had 0 rupees. Then your parents said that, okay, you are going on a trip, right? So this is the amount of money you should have. Now you went to the toll plaza first. So that took some money from you. Then you went to some shops in your trip. Then that took some money from you. Finally, you are back home with 0 money. So IR1 and IR2 are like toll taxes, which the charge needs to pay if it wants to cross the road. So from here, I got V is equal to I taken common R1 plus R2. On the other hand, if I do the same thing here, remember I told you, you cannot change voltage and you cannot change current as well. So you can write V is equal to I times Req. So if I talk about V and I in both the cases, they are same. That is something I don't want to change. So if I equate them, I'll get I into Req. This will be equal to I times R1 plus R2. I gets cancelled out. So you get Req as R1 plus. So if you have resistances in series, then in that case, you will just add all of them and you will get your single resistance which you need. For example, if I have 1 ohm, by the way, ohm is the unit of resistance. Let me just write it over here. Ohms is the unit of resistance. And this symbol here is called omega. So like you have small letter A, capital letter A. Similarly, you have small omega and capital omega as well. So this symbol here represents capital omega. Fine. And that's the symbol for ohms, the resistor. Then you have, let's say, 2 ohms. Then you have, let's say, 3 ohms. And you want to find out what is the equivalent resistance. So you will say, what's the big deal? I know I need to add R1 plus R2 plus R3, done. So that is like 1 plus 2 plus 3, which is 6 ohms. Finished. If I have, let's say, R, 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 and so on, n times, n. So what will be the equivalent resistance? R plus R plus R plus R plus R, n times. So R equivalent becomes n into R. Now, if let's say R and R are 1 ohm and 1 ohm, the equivalent is 2 ohm. Is 2 greater than 1? Yes. If I have 1 plus 3 plus 2, that is 6 ohms. Is 6 greater than 1? Yes. Is 6 greater than 2? Yes. Is 6 greater than 3? Yes. So R equivalent will always be greater than individual resistances in case of series connection. Now I'm naming it. What do we call this kind of connection? Series connection. So when resistances are connected back to back, then the equivalent resistance, that means if you replace them with a single resistance, then that value will be R1 plus R2 plus R3 and so on. So in a nutshell, what the thing is, if you have resistance in series, equivalent resistance will be the summation of it. Simple. How to prove it? Just apply money you have, toll tax paid in the first case, and money you have, toll tax pays in the equivalent case. Equate them. Done. What is the toll tax you pay? I into R. Next important connection that we have, this connection is called parallel connection. Next connection that we have, this connection is called parallel connection. Now, what is parallel connection? You will have a bunch of resistances. Let's say like this. Start with 2, then you can generalize it. And you want to calculate what will be the equivalent resistance. So you want to replace it with now understand one thing. Here the charge had 0 energy. Here the charge got V energy. Up to this point it had V energy because there are no resistances. Now it had two paths. If it goes through path 1, it will have to face resistance R1. If it goes through path 2, it will have to face resistance R2. Now, if I current is coming towards the point, some current will go in the first one and some current will go in the second one. So, if the person decides I'll follow path 1, then V minus I1 R1, that will be equal to 0. The person will come back to home. And if the person decides I'll follow path 2, or the current decides I'll follow R2 path, then V minus I2 R2 will be equal to 0. Which basically means that I can say I1 is equal to V by R1 from equation 1, and I can say I2 is equal to V by R2 from equation 2. So which leads us to I is equal to I1 plus I2. So that means I is V taken common 1 by R1 plus 1 by R2. This was the case for the circuit which had two resistances. Now I want to replace it with a single resistance. So if I want to find out what is I here, so you will say, okay, I had V amount of money, toll tax is I into R equivalent, this is 0. So that means I can be written as V by R equivalent. Now if I compare A and B, then I will get, just give me 1 second, let me shift it here. So if I compare A and B, what will I get? I will get 1 by R equivalent, because V will get cancelled out. That is equals to 1 by R1 plus 1 by R2. So if I have two resistances, let's say 3 and 6. So if I have two resistances of value 3 ohm and 6 ohm, and I am interested in finding out what will be the equivalent resistance for these two. Now I know the formula. So I'll say, okay, 1 by R equivalent is 1 by R1, which is 3, plus 1 by R2, which is 6. I'll take the LCM, I'll get 6. I'll get 2 plus 1, which is 3, 3 by 6, so 1 by 2, and this leads us to R equivalent as 2 ohms. So here, if you want to solve questions, what will you do? You will find out 1 by R1 plus 1 by R2 and finally take the reciprocal, because that is the point where a lot of students make mistake. They solve it correctly, they do everything fine, but finally they forget to take the reciprocal. So make sure you are taking reciprocal at the end. Let's take another example. Let's say I have 6, 6 and 6 ohms like this. And I'm interested in finding out what is the equivalent. So I'll say no big deal. R equivalent is what? 1 by R1 plus 1 by R2. Now I'll extend it to 1 by R3. Simple. So I'll say, okay, 1 by 6 plus 1 by 6 plus 1 by 6, which is 3 by 6, which is 1 by 2 basically. So R equivalent becomes again 2. Now, if you remember a trick here, it will make your calculations very simple. And that is if you have same resistances, right? So if R1 is equal to R2 is equal to R3 is equal to R, then R equivalent simply can be written as R by 3 if there are 3 resistances. If there are 10, then R by 10. And if there are n resistances, so if n resistances are there, then R equivalent can be written as R by n. So this way you don't have to do that 1 by R1 plus 1 by R2 plus 1 by R3 again and again. You can simply divide it and get the answer. Now, if I ask you 2, is it less than 6? In the previous case also, if I'll ask you 2, is it less than 3? Is it less than 6? Yes. So what you got from here? If the connection is a parallel connection, then R equivalent will always be less than individual resistances. Very important point. So what we learned till now, quickly, we learned charge, we learned current, we learned potential, we learned Ohm's law, we learned how to see the circuit, right? We learned how to basically apply Ohm's law in the circuit situation and calculate equivalent resistance in series and parallel combination. Now, the last two things that we'll do are basically circuit solving. How will you find out current? And last thing we'll do is power calculations. For magnetism, I'll schedule another session. Otherwise, I'll not be able to do justice to the topics that we have in here. So I'll schedule another session. In that, we'll discuss the concept of magnetism, right? So now we'll discuss something called as circuit solving. Now in circuit solving, basically what they ask, they'll give you a circuit. For example, 2 ohms here. Then they gave you, let's say 3 ohms here. And then they gave you 6 ohms here. And then they asked you, if the battery potential is 12 volts, find out the current. Fine. This is the question. Now understand how to find out the basically current in this circuit. So if you see this combination closely, you will be able to identify that 3 and 6 ohm are the resistances that are in parallel. They are connected across the same terminal, so parallel. So first what I'll do is I'll solve these two. When I solve these two, I'll get 1 by 3 plus 1 by 6, which I have solved here, and I get the equivalent as 2 ohms. So what I'll do, I'll replace these two and I'll draw the circuit neatly once again. So I'll write 2 ohms here. I'll write 2 ohms again here. And then I'll write the voltage here. And this becomes 12 volt and this is I. Then you have 2 and 2 in series now, isn't it? This 2 and 2 are now in series. And equivalent, again, we know how to solve it. 2 and 2 becomes 4. So now this becomes 4 ohms. And here you have 12 volts. So if I ask you what is the current, isn't this very simple? 12 volt is the amount of energy I had. I into 4 is the energy I gave and I came back, so 0. So I can say I can be written as 12 by 4, which is 3 amps. Simple questions, simple solution, nothing else. Now they can ask you one more thing. They can say, okay, fine, you have 2 like this, and then you have 3 like this, and then you have 6 like this, right? And this is 12. Now tell me what is the current in 3 and what is the current in 6. They change the game now. They are not asking you what the total current is. What is the current in 3 and what is the current in 6? So understand, I'll tell you a smart trick to do this. More the resistance, less the current. More collisions, less current, of course. More the resistance, less the current. So if R1, let's call it R1, and let's call this as R2. If R1 is half of R2, or you can say R2 having double resistance than R1, then I2 will be half of I1, right? So I can say R2 is what? 2 times R1. So I1 will be 2 times I2. And total current is what? 3. So if total current is 3 and it's getting distributed in I1 and I2, can I say I1 plus I2 is 3? And I1 can be written as 2I2 plus I2 is equal to 3. So 3I2 is equal to 3. 3I2 is equal to 3. So I2 becomes 1 ampere. And if I2 becomes 1 ampere, I1 becomes 2 ampere. Simple. Although I did it with maths, you can do it simply also. Total is 3. You will have to divide in the ratio of 1:2. So 1 gets 1, the other one gets 2. Simple. So I1 is 2 and I2 is 1 ampere. Last but not the least is the topic of power. So what is power? Power is rate of doing work. Again, see, the rate term is coming back. Rate of flow of charge, rate of change of displacement, rate of change of velocity, rate of doing work. Rate of doing work is power. So power can be written as W by T. And just now we studied potential is W by Q. So W can be written as V into Q by T. Now Q by T, if you recall at the beginning, we discussed this. This was I. So power can be written as V into I. So power can be written as voltage multiplied by current. Voltage multiplied by current. So if you know the voltage, you know the current, multiply them, you'll get your answer. Done. And Ohm's law says that V is equal to IR, or I can be written as V by R. So if I substitute instead of V IR, I'll get another formula for power, which is I square R. And if I substitute I as V by R, I'll get one more formula, P is equal to V square by R. So in totality, how many formulas are there? 3. Number 1, V into I. Number 2, I square R. Number 3, V square by R. So if you know current and resistance, you apply I square R. If you know voltage and resistance, you apply V square by R. If you know voltage and current, you apply V into I. Generally, in series combination, you will be able to calculate voltage, currents easily. In parallel combination, you will be able to calculate voltages easily. So depending on what you know, you can find out power using I square R or V square by R. All the formulas can be applied in any given situation. Now the unit. So power we defined as work done by time. So it would have been joule per second. But again, like any other unit which we studied today, this also has another name. It's called watts. Fine. So the unit is watt actually, but for plural watts. Now, sometimes they ask you what is the heat energy dissipated. So understand, power is work done by time. And work done is a form of energy. When the electron passes through a resistor, basically, it collides and releases energy. That's a form of work done which is getting released in form of heat. So work done can be treated as energy. Here H we are representing with heat energy. So this represents heat energy. And we know that power is W by T. So that can be written as H by T. So that makes H P into T. Or it can also be written as I square R into T or V square by R into. Unit of energy, you know, it's joules. But from here, you'll get another unit. What is that unit? Power's unit is watt. And you're multiplying with time. So this can also be written as watt seconds. Some other units of heat energy are also there. For example, if we take power in kilowatts, then your heat energy unit becomes kilowatt and time in hours. So multiplied by. So another unit for heat energy is kilowatt hour. Kilowatt hour. And 1 kilowatt hour is equal to 1 unit that we use at home. When you see your meter, right, a red light blinks and the numbers on the screen changes, right? So that is what you call number of units because that decides your electricity bill. So when you consume 1 kilowatt of power in 1 hour, then the reading changes by a factor of 1. So what kind of questions come? They will give you that, okay, there is a fan and that fan consumes 2 kilowatt and works for 10 hours. So 2 kilowatt multiplied by 10. So 20 kilowatt hour. That means electricity bill due to that is 20 units. Although the fan doesn't consume that much. Let's say air conditioner, 2-3 air conditioners are there and they are consuming some kilowatts for certain number of hours. Again, you will multiply kilowatt into hour. Again, you'll get the number of units. Then what they say, if this happens for a month, then you'll multiply that with 30 or 31. And you'll get the total number of units you will consume in a month. And then they say that, okay, 1 unit costs 6 rupees. Then they say 1 unit costs 6 rupees. So you'll multiply the number of units with 6 rupees. So the overall calculation will look something like this. So first of all, you will calculate the number of kilowatt hours you got. Multiply this with number of hours per day multiplied by number of days. And then multiplied by unit cost. Like 6 rupees, 10 rupees, 3 rupees, whatever. And that is your electricity bill. Electricity. One very common unit of power is horsepower as well. Although it's not the SI unit, and that is 746. But don't worry, this has nothing to do with the unit calculation that you have. So I hope everything that we discussed today was clear. And for magnetism, I'll take another session and then we can complete magnetism in there. If you have any doubts and you want to share anything, please pin it down in the comments and I'll surely get back to you as soon as possible. Till the next session, I'll see you guys. Bye-bye. Take care.